Hello everyone, and welcome into yet another live stream. And I'm going insane. Give me a second, actually, to prepare the stream. But I am going insane. I started the stream so suddenly because I am just straight up going insane. You see, I've been working on this thing, on this thing, guys. Rather not rather known to anyone who's watched my live streams, which means to no one. This thing called hyper-operational mathematics, and I've just gone insane. At this point, I'm just going in. Yeah, that's it. I've gone insane. You see, I've been working on this for so long, for a really long time, and I did nothing. Up to this point, I did nothing. I achieved nothing. So today, we will try to achieve something. You see, I mostly been stuck on the omega delta problem and the half functions. The half functions were such a disappointment because the half function was just an anti-operation, which is disappointing. But but there's one thing. I actually should rename the stream from I'm going insane to something less exciting, less clickbaity. The hyper-hypo problem. That's what I'll call it. Basically, there is one thing that is extremely important right now. Because here's the thing. Hyper operations are cracked by definition. By definition, they are done, they are the base, so yeah, finding the relation between hyper operations is a piece of cake, so that's easy. Anti-operations are also a piece of cake when you consider that anti-operations are just negative numbers with that are just hyper operations operated on a negative number. Then they are also a piece of cake, obviously. I mean, extremely easy. The only one pickle remaining from actually not solving the puzzle. Okay, that's not the last piece of the puzzle. It's kind of the last thing we need in order to start solving the puzzle are the hypo operations. Unbelievably important. And hypo operations and anti-hypo operations are also the most mysterious ones, the really weird ones. Now, okay, over here I also have open Space, Life and Time, which is a paper that I started in order to get a break from hyper-operational mathematics. And over here I have a Desmos file because, as I said, I've gone insane. I've been checking these things for I don't know how long. There is no automatic way to do titration in Desmos, so I have to kind of do it manually. By the way, here you can see different hyper operations to the third. So first hyper operation to the third looks like this. Here's the second, here's the third, here's the fourth, and that's it. That's about as far as Desmos will let me go. Yeah, cool, am I right? 2 perhaps would be more clear. There we go. Great. Great. Fantastic. Now, the three most, well, okay, so I should probably draw a map of what's important, or actually at least show you the map. So here's the thing. The end goal, for now, the end goal would be to solve the omega delta problem, which is my arch nemesis at this point. Omega delta problem is my arch nemesis. In order to get some tools in order to solve the omega delta problem, we should first of all, because as you can see, there are no hyper operations here, because I have no idea how they work. So in order to solve the omega delta problem, two things that could really come in handy, three things, actually now I'm thinking about this, is first of all, negative numbers. The negative function, cracking the negative function would be great. If we could crack the negative function, then we're in business. Then, because this would basically give us a key to understanding all the anti-operations. OHATs, extremely useful, because O hats would tell us, well, what we are looking for. The end goal is to set delta equal to to the O hat n, some O hat n. So yeah, that's also very important. And then the third thing, which we'll start the live stream with today, are the hypo operations over here, which you might have noticed, hypo operations are the only things that do not show up, that never show up again. Over here we have, those are hyper operations with, you know, different notation. Anti-operations, hyper operations, and only over here as an example of as a definition of a fixed point. So yeah, it's great. Also, one interesting part about the fixed point that I have only now noticed is one really interesting thing about the fixed point is that it works when it's anti-operated, right? Because the first root, for example, of any number n is still n. Let me actually paint. Paint, come help me out here. Paint. So, for example, for fixed point, for all of them, for addition, I could just say that as an array. That would be more convenient notationally. Addition, multiplication, and there are ones after it, right? I'm pretty certain the rest are just ones. Again, we cannot be sure if the rest are ones, right? We are not sure if the rest of fixed points are ones. Well, logically it would make sense, but it's hyper-operational mathematics. It don't make sense. So yeah, unless I prove it, I'll just have to write it. So we know that for titration is 1, for exponentiation is 1, for multiplication is 1, and for addition is 0. So that's great. So now 1 minus 0 is, well, not 1. Let's do general. N minus 0 is equal to n. That's how we know. So it's a fixed point. N divided by 1 is equal to n, fixed point. N first root is equal to n, fixed point. And n hypertitrated, I do believe this, so we didn't know that before. I mean, hyper anti-operated, I don't know, is n. Makes sense. So now what we can do is, well, one really interesting thing, yeah, that's what I was about to mention, is that if that's the case, right, with fixed point, if this is still equal to a, and this is the negative version of a fixed point, that means we can also note this as, that's kind of funny. I started the stream by saying that the three most important things are O hats, negative functions, and the hypo operations. And right now I'm doing none of them. I'm just doing fixed points. So that's funny. This would be equal to a up arrow. Also, let's generalize this. More convenient. Doing generalized equations is harder, but it's, well, better objectively. This to the negative in relation to n, negative of x. No, wait, that's equal to a. So this is the, because this is down, which means this is negative to n, definition of the anti-operation. And this should be, by the way, y over here. I almost screwed that up, which means it's up to the fixed point, n. I feel like that may be the universe giving me some kind of foreshadowing, but at the same time, as I said, I have gone insane, so I don't know, at this point. Might be true, might be not, might be useful, might be just another notation rewritten again. Huh. There's one thing that's pretty interesting about that. And that's this. That's interesting. Because normally this should look different. Also one thing that's really interesting, so based on the negative number definition of anti-operations, we can conclude that. Also, I can also write a proof that there exists a fixed point for every hyper-operations, because that won't be that hard. It's just when you are hyper-operating, you have the negative function, right? Which means when you have a negative function, right? Which basically means that, let me show you what I mean with a couple of anti-operations. So we'll have, for example, 5. Let's use 5 for this. 5 minus x, right? Then we have 5 divided by x. Would this be? No. We need hyper-operations, not anti-operations. 5 plus x, 5 times x, 5 to the power of x. There we go. This will do fine. Now all we need is one more line, which would be 5. Y is equal to 5, right? Yeah, there we go. And now we can see that for all of these hyper-operations, there are numbers, there are specific x's which add to it, which means they make them larger, and there are specific x's which make them smaller. Now these smaller ones would be anti-operations, so these are the negative number versions of the thing. These are so for example, for subtraction, that would be all the negative numbers. For, well, multiplication, well, for division, actually, those would be, negative numbers, yes, but that's only because we went in relation to 5. We could also go with a 0. No, 0 would break. For division is basically in between 0 and 1. Basically, we do not count the negative version over here. It's, well, we do. It's complicated. Complicated relationship. Same with powers. It's actually very interesting, because negative means basically division, right? 1 divided by x. Yeah, because this is just 1 divided by this, like flipped. So yeah, there exists a fixed point for every single one. Based on that, I could do proof of that. I will not, because as I said, I don't want to waste time for now on fixed points. But this is especially interesting, because you see, we can add as many fixed points to the end as we want. Also, this is equal to a. Wait, this is equal to a. This is equal to a. Up arrow. And this is equal to a. Which means that in this case, this is equal. Now that's interesting. And yeah, it is. If you think about it, yeah, it is. N plus or minus 0 doesn't make any difference. N times or divided by 1 doesn't make any difference. X to the power or rooted 1 doesn't make any difference. But it is interesting because it would mean fixed points have some specific quality, because this is only true for fixed points. Only true for fixed points. Where negative in relation to the wait. Whoa. And over here, I'm about to do something for which I'll have to elaborate on, and for which every mathematician will think I'm insane. But it's not that much of an issue. I am insane, and I am. What I'm doing here is not really smart, so I'm not expecting this to make sense. Because what it means, basically, I should probably delete those ends, they look weird. But I will have to figure out a way to make this work, which basically means equality in relation to hyperoperations. That's my only idea for now. That's interesting. And it makes sense. It does, kind of. Does it? Wait. Does it? It's not. It doesn't. Yeah. For any negative number, it's undefined. Well, logarithms... I'm pretty certain Blackpen Redpen had a video where he basically extended logarithms to the complex plane, and then there was an equation for calculating logarithms of any sign. So in some relation, negative numbers are just the numbers on the other side of the fixed point. So we have negative numbers in relation to hyperoperation, we have positive numbers in relation to hyperoperation, and we have a fixed point which divides them. Which makes sense. It actually does make sense, because then positive numbers for for multiplication, for example, are from 1 up. From 1 down, those are the negative numbers in relation to the multiplication, and 1 is the fixed point. Which means we just found the domain for negative numbers. Okay, I have to write it down fast before I forget. The fixed point is especially significant if you consider the negative and positive numbers in relation to a given hyper operation. Considering the fact that all hyper operations are continuous, I misspelled that, please fix Google. Continuous, we can conclude that, okay, how to write it down so I won't forget. All the negative numbers all the negative numbers in relation to a given hyper operation exist next to the positive numbers in relation to all the negative numbers. Okay, so it will be just, because that's getting really wordy, exist next to positive numbers and are divided by a fixed point. That is some insight. Continuous. There we go. That is some insight. It's not particularly useful, but it is decently useful. On a scale from 1 to 10, it would be solid 0.5 in terms of usefulness. Well, no, in terms of usefulness, it will be a solid 3. In the terms of a breakthrough, it will be a solid 0.10, but you know. Based on this fact, we can now conclude describe the domain of all negative numbers. Okay, that is a bit better, not gonna lie. Okay, this is actually pretty interesting. Or maybe it's interesting to me, only to me, but because all the negative numbers then, so what would be our notation for, it would be omega of n, just negative? No, that seems wrong. Okay, I don't mean to go so quantum physics operator like, but okay, so then could this pass for no, Greek symbols. Greek alphabet, we need to find something better. Greek alphabet. What screams negative, set of all negative? Chi? It's tempting. Alright. Chi of n. Domain of all, no, it has to be omega based. What am I doing? Yeah, I'm terrified absolutely to note this because this is actually the first thing that could be somewhat useful. We found the domain of a function. We found the domain. That's the first step or the last step of finding a function. For me, it's a first step right now, but sometimes just do it last after you know everything about the function. So this is in omega n. That's first of all very important thing to mention. And then the logical operators, right? So basically, bar hat O n is equal to, is smaller at fixed point. Smaller, okay, but we have to change that so that smaller in relation to hyper, okay, or maybe just smaller. Where this okay, this is actually kind of sick. We found the domain. We found the domain of the negative numbers in relation to any given hyperoperation, which is neat. Now the only problem is finding the actual negative function. How hard could that be? Could be very hard. Could be very much hard. Because there's not much I can go off. Also, there's one very important question which is annoying me very much. When you have 5 times x, right? Any number here, like for example 0.5, right? 0.5 over here just mean is equal to 5 divided by 2. The problem that I have right now is, are these negative numbers in relation to multiplication, or are just these negative numbers in relation to multiplication? We could say that multiplying by 0 means end of all multiplication. That would be a very controversial thing to say. But it would make sense. It would eliminate all really weird things, but at the same time, it would kind of, yeah, it would delete every single imaginary based thing, which is not good. It's very much not good, considering how important imaginary numbers are. Like, if we do that, then we cannot use the sine function or cosine function or anything based on that. So yeah, it's not a good idea. But we could say that everything below 0 is imaginary already, considered imaginary, and by considered imaginary I would mean that I'll deal with it later, which is a terrible idea actually, retrospectively. It would be really convenient if I could say that these are doubly negative numbers. But I can't. Can I now? Music, great idea. Quite what I was thinking. So how about this? Okay, maybe not. Oh yeah, I remember when I was making multi-up with this mixtape in the background. That was good. It's good. Listened to it for 60-70 times. Great. Okay. Cool. So where are we standing? I am. All right. Let's give this up for now. The negative function. It's very tempting. If I could solve negative function, smooth sailing. Then we would have it. If I could describe negative function in relation to only hyper operations, I mean, that would be great. But we can't really. We had one candidate, which was the x to the n plus 1 to the negative 1. It was a decent candidate. Candidates for the negative function. These candidates fit the negative function requirements, but are not considered negative function until proven. One, which is the very lovely, beloved by me, is equal to x up arrow, obviously in relation to n, cannot forget about that, that's very important here, n plus 1, up arrow, negative 1. I love this one. I mean, it's beloved by me very much. But we do not really know. Well, we do know that it's. We didn't prove that, is what I meant. Why am I stuttering? My goodness. As I said, this is driving me nuts. So we should just focus on the hypo operations at this point, as they are still very much lost. Okay, numbers, no operations, generalization, and below the generalization we will add hypo operations. Very much forgotten, but really important. Mostly forgotten because of the fact that hypo operations in conventional working normal mathematics are only expressed using the logarithm, and there's nothing for the anti-hypo operations, which, you know, is really sad. So wrong font, thank you. Hypo operations. Okay, let's first think about this. We once again shall use decimals because obviously it's very helpful. And let's just use hypo operation the second, right? So we'll use this and log to x. Those are lovely two hypo operations. It would be described as x2 is equal to y and 2x is equal to y, and we can consider what that actually means if we extend it. Actually, okay, technically it would look like this because we are talking about exponentiation here. Now we can technically think about what that means. Well, not technically, it's AB. Actually, we shouldn't do ABC, we should change that a bit so that it will be easier to think about. So when we have up arrow, what we are asking is to which number we bring A to get C and it's equal to B. Which means if we want to unwrap this, oops, not what I meant. Which means if we want to unwrap this whole thing, we have to do y is equal to 2. And then the second one, which is 2 to the y is equal to x. Those are our two equations. And as I said, hyper operations are the most annoying ones because first of all, they are just straight up complex. It's well, not straight up complex, not complex, imaginary complex, but they're not simple. They're very tough. It's hard to predict them. They have very weird. They are weird. They're just really weird. And because of that, it will not be easy to. Well, obviously, the end goal, just like with anti-operations, would be to create a simple equation for them. That goal is very much unrealistic, so I don't know if I will attempt. For now, I'm just trying to understand them better. Let's also add to the mix, to complex things even further, let's add the anti-hypo operations. Oops, sorry about that. Down arrow. The anti, which in normal mathematics are not used in the slightest. They are not used at all. But still very useful functions indeed, because they're as useful as normal hyper operations, because why wouldn't they be? Which means that over here all we have to do is just exchange that for down arrow, which means anti-operations in this case, in this scenario. Great. Now it's time for the actual fun. Yet I know there are a lot of arrows on the screen, a lot of stuff going on. It would be really easy to get confused. But I will try to fix this as soon as I can. First, let's generalize, because as always, generalization, great thing, really convenient, which means we'll do it for any operation. What's also really convenient is that... Okay, I'll mention that later. For now, let's just work on this. So, anti-operations, we can already describe anti-operations in relation to the negative function, right? Which means this could be equal to 2 up arrow n up arrow y, but not y, only obviously the negative function y. There we go. That's what it means. Now, I think I just realized one thing about negative numbers too, but okay, that's for later. Don't get distracted, you are doing hyper operations now. So, now we can describe it like this. What's really convenient is that we can show the relation between hyper and hypo operations. So, in this case, yes, y is what we are looking for. Which means, where's this one? It's this one, right? Yes, it's this one. Yeah, there are a lot of things on the screen. I should probably... Okay, it doesn't matter which one is it to, so I'll just work on these two, okay? So, the place where the 2 is first. And I should probably do ABC. Well, I know why I made it so hard for myself. AC is equal to B. ABC notation is very convenient because then when we are doing this, I can just do A, B, C. Simple, alphabetical order, great. A, B, C. Is that correct? A to the power of B is equal to C, so we are looking to which power bring A in order to get B. It is correct, great, sick, wonderful. Now, A, B, A, B. This seems like no progress, but it is actually progress, because right now we can describe both of these as hyper-operations, and hyper-operations are just straight up nicer to work with. Also, I don't really like this ABC, and that doesn't matter. Which means that, there we go. Think about this. Which means that anti-hyper operation is just equal to normal hyper operation, but negative. So pass through the negative function b. Well, not quite that. This. Wait, is that correct? Okay, so this is still equal to for the hyper operations, which is very convenient. Right? Okay, I'm really scared that I made some errors right now. We should ditch the ABC this way. We should do it with the negative. So bar B to symbolize negative, bar C. Yeah, we'll have B and bar B. Yes, and now we are looking for the relation between them. Now we know that this and over here it will have a bar because it's the negative version, will give us C. Yes, and now we know that anti-operated bar B, that's is just a negative version of B. Bar of B. And now that we know that, we can just say that it is also equal to the up arrow version there we go. So this, I'm really complicating things here for myself. Okay. B is equal to just the same thing but negative. Great. Now what that means is that this is still equal to C, which is convenient. Now if this is equal to C, then what we can do is we can take this, which is to C, right, and put this inside for C. Yes, but very important, brackets. Remember that it's just number there. Great. And now the rules for hyper operations could really come in handy, something that I should have started with. Okay, I've gone insane, as I said, okay? My brain's mush at this point. Not... Actually, first, rules of hyper operations. This music is killing me, I'm sorry. It's great, obviously, but I just listened to it for, right now I'm listening to it for the 100th time. and I'm not exaggerating even at this point, which is the sad part. Actually, it's probably more than 100th time. I had like 200 streams from MKT multi-app alone, and in each and every single one of them I listened to this playlist. The quiet, it's so nice. Okay. Hyper operations. Rules of hyper operations, we can get them based on normal rules of normal operations. So first of all, obviously we are going to generalize, because generalizing is annoying, but it is useful. There we go. So now, what? Well, now we have this. We are going to check how this will do for different things. So for example, over here, if our C is equal to, what? C is equal to, for example, A down arrow N down arrow B. First let's do it for up arrow, down arrows. Yeah. Down arrow seems like the most of this step. So if this is equal to this, actually no, up arrow. Yes, up arrow will be the easiest one. If this then is equal to this, which gives us nothing. We can anti-operate, well, yeah, it gives us nothing. Which means if C is equal to, if C is equal to A, I've operated NB. Yeah, let's do down arrows, that will be. Yeah, because this gives us nothing. Well, not nothing. Nothing is something in this case. It will be easier to consider this with normal math. Log x, y, a, c is equal to b, right? Then a to the power b is equal to c. And if c is equal to a to the power b, that means a to the power b is equal to a to the power b, and in this case log of a to the power b is equal to b, so it does tell us nothing. Yes. So for this equation, which means that a and b are in omega n. Actually, no, it means that A and B is that N, which means that any A and B solve this equation. Is there a case where this would not be true? No, it is true. By definition, yes. Cool. Now let's check another example. This time a bit more complex. where this would be down arrow. There we go. C is equal to A down arrow B. And for this, I would prefer to switch it to anti-hypo operation. That would be more convenient. Which means that we can up operate on both sides. And over here we would get A, over here we would get B and up arrow B. Which should mean n+1? Do I not have rules for normal hyper operations here? I don't have rules for hyper operations here. No, I have. Oh, okay, it's this. I have only evolution. Well, that explains a lot. Rules of hyper operations. Now the first rule of hyper operations, which I would prefer to discuss actually, is the twos, which basically means, that's good enough, 2 up arrow n up arrow 2 is equal to 4. And in order to start this, we will need this. There we go. So I'll give you some space. We would need this. 2 is equal to 4. Now 2 to the arrow is equal to arrow n, like this, is equal to n plus 1, which means that for any n, for any n is equal to 4. This is a very short proof, but it's a simple one, and it might be convenient because only 2's work this way, which is very fun. For 3's, this is a different case. It's surprisingly different. Yeah, so over here, based on the most basic of rules, right, because we seen this, based on this, we can say that this is the case. Very handy indeed. Now let's try it for 3's or any other number. Now for 3's we obviously will not try it the same way, or actually let's leave it blank for now and let's do x. So this will be the same as this, only generalized, hopefully. Which means that based on this, obviously, n up arrow x dot 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 up arrow x. There we go. So now let's try it first with 3's. Simple way to try this. 3 plus 3 plus 3 is 9. Great. Let's try it a couple of times to get a sense for a pattern to see what we are actually looking for. 3 times 3 is equal to 9 times 3 is equal to 27. 3 to the power of 3 is equal to 27, and 3 to the power of 27 is a ridiculous actually number, you will not believe. Python 3, 3, 3, 3. Yeah, it's ridiculous. It's absolutely bonkers. I try to make the table. I try to make a table with all those numbers for different hyper operations, but for tetration numbers are just ridiculous. They are just ridiculous. So yeah, this is 3 to the third power to the third power. In case anyone's wondering, it's very fun. Now. What can we conclude based on this? 3 is evolution 3. 3 will be 3 to the third of n plus 1. Which I mean, yeah, that is true. I suppose, yes. So in this case, yeah, okay, that's still pretty obvious. Actually, it's so obvious that I'll switch it to the first one. Up arrow N, up arrow X, up arrow N, up arrow dot, up arrow N, up arrow X is equal to, so I should probably add here, is equal to X up arrow N plus 1 up arrow X. I don't know when it will come in handy, but it might, so I'm just saying. Based on A plus 1, this and A to the A 3, or basically any in the yeah, whatever, it works. Then we have next one, which is the anti-operation operated on hyper-operation. Actually, no, that's a definition of anti-operation, so I guess within there, what will come in handy then? Oh yeah, good one. Now I remembered why we're doing this. This, obviously. But in this case, we need something different. Not A on the X. That's what we need here. And now this is a bit more tricky, ever slightly bit more tricky. It's basically, this is very tricky for one reason mostly. We have only 3 operations on which we can experiment. It's addition, multiplication, and the exponentiation. The problem is 2 of them are commutative, which sucks. It sucks because we need the non-commutative ones, which means these are kind of useless. What do the commutative ones tell us though? Well, we are going from up down, which means this is just A to the B tetrated. So it does work. We are going from the up down. That's actually very convenient. Yeah, this is tetrated, obviously. Oh, but in this case, we are not going from the up down, are we? Yeah, that would be too easy, wouldn't it? Great, that would be way too easy. We are going from the down up. I hate that fact. Yeah, it's not good. It's very terrible in our circumstances. It's very terrible. So what's A, B, tetrated B? Because this is what we need. It's not non-commutative. It's exactly what we need. We could obviously do quaternions here, but that would be a bit of an overkill, don't you think? Great. So, what's A to the B tetrated to the B? Yeah, it's not, no, it's not good. When it comes to this one, obviously we can solve it. X is equal to A to the B, and the obvious X, well, and the obvious trick with natural log. It's equal to B natural log of A to the B. Actually, yeah. And then we could take down another B, actually. Wait, am I wrong? Can we not? Okay, in one of my really old papers, well, it wasn't a paper. It was not a paper, it was just a document that I had. I'll have to. Nope, that's just the thing that I used. The boat fender, no. Not the boat fender. William Shakespeare's fun. This one. Most basic derivation was yes. We need to turn this equation into the formulas for this, so yeah, multiplied all of them, and then we get x to the x to the n. X to the x to the n, which means that for, and this is going from down up. That's why down up is usually the easier case, because obviously we can just collapse them. I don't know why I felt the need to. Excuse me, Windows, you mind? I just want my paint. Can I have my paint, please? Thank you. I only had to disintegrate my entire right screen to get it. Great. Which means we can obviously consider that as A to the B squared, like this. But the question is it, can we generalize that then? The question then is A tetrated B tetrated B? Does that still work? That's what's so annoying about this, isn't it? Well, actually, this way, there we go. Does that still work? Alright, let's consider some simple examples. Right. So in this case, this is equal to 2, 2, 2, right? That's 4, 4 squared, 16, 2 to the 4th, 16. Great. Now once again, some simple examples, right? Don't overdo it or anything. So let's do 4 to the third, to the third. This should be equal to 4 to the third squared. And if you consider this, then you get Python, where you at? Thank you. 4 to the third power, to the third power, first diff, and 4 to the third to the second power. First diff, it works. Great, Grant. Now all we have to do is we have to do the same thing for titration. Is it titration in Python, by the way? There surely is some mad lad who did a package, right? Okay, there's someone who just did titration. Can I paste it in? I guess that means no, because I have to define titration of x and n this, and now I have to paste the definition. I guess not. Fine, I'll do it with... fine, I'll do it with just code, like a normal person. CD desktop projects. Well, it's not hyper operational. Don't I have one? No. Make the hyper CD hyper code. I'm really surprised there isn't a package in Python which you can just import. tet.py. Good enough. And now I suppose I can just use it, right? Python. Okay, maybe I have to use still code. Great. Fine. Because it's hard coded, isn't it? Excellent. Just ask for input. Might as well. Input x, also very important in Python, always to remember, is that it will treat as a string, which is not something that we need, no want. And great. One simple fix. And now we can do titration, which is once again very festive. Kind of. Well, it will tell us if it is true in some cases, won't tell us every single case, and definitely will not tell us about rational numbers, nor about the irrational numbers, and about transcendental or omega 5, we can just dream. So that's great. Fun. X. Our x will be equal to... Actually, we kind of need... Wait, can we do Python import tet.py? Can I just import titration of x and like free set 2? Damn it. If I could import that, that would be way better. But fine, we'll do it this way. Let's titrate. Ditch this, might as well. And now what we need to do is we need to check if titration of x to this is equal to the other side. So for example, let's do 4, 3, 3, right? Now Python titration py. It broke. Okay, it might. Okay, I can see the problem considering that titration like this might be pretty. X is not defined. Screw the X. Just do the T. Like this. Yeah, I can see. I can see why. Yeah, I guess the iteration to the third. Yeah, it's 3 to the third to the third. Yeah. I guess I can. Fudge. Oh, we are so handicapped with this. We do not have the computational power for this, which is insane. When was the last time when you wanted to do some basic math and you didn't have the computational power required? Fine, I guess we'll just have to expand iteration. We'll just have to do it by hands. So 3 like this. The question is it equal to this, which will be 4, which will be 3, 3, 4. That's the question. Let's expand it by hands. That's fun. Am I right? Is it not? Oh, it's not. Doesn't matter. So first of all, 3 is raised to the third. That would be 3, 3, 3. There we go. 4. And the question is it equal to the third iteration of 4, 4, 4, 4? Actually, wait, this third. Yeah, there we go. That's the question. In order to expand it again, we would need to. Well, we can expand this, right? That's, I suppose, which would be equal to this one. It would be 4, 4, 4. 4, 4, 4. Okay, let's set it to x. Let's set this to be an x. Then we have x to the x to the x over here. And over here, we would have a lot more. It would climb up. Well, I think this one is greater, honestly. Because on the right, what we would get is we would get 4, 4, 4, 4, 4, 4, 4, 4, 4, right? On the left, what we would get is 7 billion fours? I think a lot more. Okay, it's great. No, it's festive. Fantastic. I'm looking for the thing that I did wrong. I had to do something wrong, right? I mean, let's be reasonable here. 3 to the third is an outrageous number. It just is. It's outrageous. It's large, very large. So bringing 4 to this number that's rated, that's a ridiculous idea. And my PC would genuinely crash before it could compute that. We would have to recurse so many times, so no. On the other hand, this, we can just check. We have this iteration, right? So let's check if we did this, what would happen? It didn't hit, so it's not equal. It didn't hit the limit yet. I can hear my PC now, it's screaming for help. But it didn't hit the limit. Okay, tell me what this is first. 4 tetrated the third. It's a massive number, yeah. So then what we do is we tetrate that by itself to the third. So it's this massive number tetrated to the third, or this massive number to itself to itself. On the other hand, on the left side, we have 4 tetrated like this. So now the question we should ask is, A, B, what's its relation to B, A? Which one's bigger? Because if this one is bigger, well, which one is bigger if B is greater than A, for example? Logically, it should be this one. Because that's the scenario we're in. Actually, no, wait, that's... Right? Yeah, that's the scenario we're in. 4 to the 4th to the 4th is larger than 3 to the 3rd to the 3rd. So the only question is now, which titration is greater? So we can check that. We can check that with 2 third and 3 2. Right? One of them will be larger. Yes. So 2 3. Logically, it should be the one where tetrational number is bigger. Yeah, so, yeah. Wait, x to the n. So it was the other way. Once again, there are also some cases in which it's equal, which is even more annoying. Fudge. But they are not equal. They shouldn't be. They shouldn't doesn't mean they are. Doesn't mean they aren't. Oh, fudge. Why is it so difficult? I'm just asking which one is greater, A, B, or BA. I just don't know. I'm lost. Okay. Wolfram Alpha. Please tell me you have titration. If you don't, I'm doomed. Do you or do you not? You do not. Or maybe you do. I'll just have to use... I feel like I already checked that. Great. Neat examples. Well, ain't that neat? Okay, so it... I have no idea how functions in Wolfram Alpha will look. What they look like. If I have an integral of x, this integrate... Okay, so it's square brackets. So it should look like this. No. Tetrate? No. Fudge! Kind of with an online client because I don't want to set up Wolfram Alpha on my own. That seems like complicated. I'm not that much of a computer scientist. I don't have willpower to do that. So the general rule is AB is not equal to BA. Well, that doesn't help us actually because that gives us nothing, and it's not the kind of nothing that would give us something. No, it's just nothing that would give us nothing. I don't know. we got the domain for the negative function, but on the other hand, it was really obvious. I don't know. I just don't know. Let's try with 2 and 3, because those numbers will be smaller. So, 2, 3, 3, right? What's the relation to 3, 2, 3, like this? Yes. This one is different. Understand? Because there's a difference in between commutativity and associativity. I definitely mispronounced that. But basic idea is 3 to the third over 2, like this. And 2 to the 2 to the 2, yeah, that's has to be different. Maybe it isn't. I can tell both of these numbers are even, which, you know, is obvious. But the left one is definitely larger, right? Because that's 2, 2, 2, 2, 2, 2 so many times. On the other hand, on the right we have 2, 2, 2, 2, 2, 2, 2, 2, 2. There we go. So this one is definitely larger, because over here 2's go on forever, practically. Not forever, obviously. It is finite, but it's a very large number. Rather large number, because it's Python. That's the number we're dealing with here. So it's a lot of 2's. So this one is definitely larger, which means that there is absolutely no rule for this scenario, which is festive. It's very festive. I feel like with every single hyper operation, we are losing some tools. For example, addition is extremely easy, right? There are so many nice things. Then we have multiplication, which in quaternions loses commutativity. Then we have exponentiation, which loses it for all the numbers. Then we have tetration, which is not even understood. Also, we don't have any graphical interpretations of this. In normal mathematics, there are graphical interpretations for everything, but like every single dimension is just taken by the exponents. So things that are beyond exponents, that's just insanity. Is this my way of saying, like, I'm done giving up? I cannot tell. I don't want to give this up, but it's so damn difficult. I'm such an idiot. I haven't done nothing. I have done nothing yet. There's nothing that here. Yeah, I think it's time to give up on hyper operations. I feel like I could define them. I could define them in a way which would make this entire thing possible, but then they would be useless. Because in order to define them in the way that would be possible, I would have to redefine not only exponentiation but also multiplication, which would mean it would be useless. Yeah. If you think about this, if you take an exponent, right, to a zero, so n to the zero, that's equal to 1. But it shouldn't be for the hyper-operational case. In normal mathematics, obviously, it's very useful, very important. But for hyper-operational mathematics, it really shouldn't be, because if you take an up, for example, 3, let's say to the 4th power, that would be equal to 3 times 3 times 3 times 3, right? But on the other hand, what that means is 3 plus 3 plus 3, right? Plus 3 plus 3 plus 3. And then all of this also 3 times. And all of this also 3 times. I should have picked an easier example like 3 to the second. 3 times 3, which basically is 3 plus 3 plus 3. There we go. Right. And so if we go for 3 to the first, that's just 3, that's just 3, and 3 to the 0th. Well, in normal mathematics it's 1, which makes sense and is very useful for exponentiation rules. But it also means that for there will be one addition case. Makes sense because over here we are every single time dividing by 3, right? But addition is already lost. Rules for addition in this case are then dependent on these. When it comes to addition by itself, it makes no sense. So yeah, it's time to give up. It's time to not waste any more time on this. I still have space left and time to write, which will be probably more important. It's fine, I only wasted like, I don't know, a week or 2 weeks on this. Yes, I'm not mad. Why would I be mad? Well, that was festive, wasn't it? Great, so thank you everyone so much for watching the I'm Giving Up stream. And I'll see you in the next live stream. So yeah, thank you everyone so much for watching and have a great day. Bye!